Pickup trucks represent the top 3 best-selling vehicles in America. Why? Trucks inspire a connection and involvement with the space around you. Whether it's hauling bicycles, house paint, construction tools, garden mulch, or camping gear, the way a truck empowers you to own and to be a part of your environment is like nothing else on the road. For this reason, IDI is investing in empowering technology to bring about the next generation of the truck bed. We're also taking what we learned from there and evaluating how it can be applied to the electrified powertrain. I'm Rob Holcombe, Product Manager for IDI. At the end of these 20 minutes, you'll know who IDI is and where we fit in the value stream to the automotive market. I'll explain what Fortium QISO is, how it's made, and how it's used. You'll understand how Fortium QISO answers the promise of a next-gen pickup box, as I detail a joint development effort between IDI, a major automotive OEM, and a global engineering consultancy. You'll see how this technology can empower and inspire designers with its flexibility, and the ways it can be extended into other vehicle domains such as battery enclosures, body shielding, and localized reinforcement. IDI is a global leader in formulating and manufacturing thermoset molding composites. That is, we design and produce sheet molding compound, bulk molding compound, and now a pre-preg co-molding compound, the topic of today's talk. Our global headquarters is located in Noblesville, Indiana, and we have technology centers and manufacturing sites in Mexico, Puerto Rico, France, the UK, and China. Besides automotive, we serve electrical, construction, and infrastructure markets the world over. We maintain a commitment to the composites industry through our collaborative and creative efforts, investment in growth and research, and a long-term vision for our place in the market. Fortium QISO is today's topic. The name Fortium may be new to you, but its application may be surprisingly familiar. It's the black, discontinuous, fiberglass reinforced composite that comprises the bed of many modern small trucks. Fortium is resilient, standing up to harsh weathering, ultraviolet radiation, chemicals, and all the abuses expected in the daily life of a truck, thanks in large part to its resin chemistry. Today, I introduce you to a triaxial braided product called QISO, developed by our friends and partners at A&P Technology. QISO stands for quasi-isotropic, referring to the more consistent properties gained by using 3 non-orthogonal woven biases. As opposed to the conventional woven products with 0 and 90-degree fibers, QISO introduces a third axis, offsetting each by 60 degrees. QISO's superior performance to 0-90 has been demonstrated in fiberglass and carbon fiber and in various toe sizes. QISO, as a braided product, also offers much better drapability than conventional 0-90 products, which is vital in the compound curvatures found in compression molded parts. The field-proven performance of Fortium, combined with the quasi-isotropic strength of QISO, offers designers an unmatched level of design flexibility and robustness for the next generation of vehicle performance. Consider a conventional SMC line where chopped fiberglass rovings are combined with a thickened resin paste and compacted between 2 sheets of film. By replacing the chopped rovings with QISO fabric and impregnating it with the same resin system as Fortium, We generate a chemically perfect match for co-molding our discontinuous SMC Fortium with continuous fiber prepreg Fortium QISO. The resulting prepreg was designed to have the same fiber loading by weight as the SMC, meaning the same density. This simply means that in prototyping, if you wish to add 1 kilogram of QISO to cover a certain area of high stress, you simply remove 1 kilogram of SMC from the charge as a starting point. QISO charges are cut just as easily as SMC, they are laid in the tool just as an SMC charge is, and they cure the same, meaning no major process changes. Because of its quasi-isotropic properties, QISO is also less sensitive to the precise orientation or placement in the charge by operators. A final benefit to the quasi-isotropic properties is the flexibility in orienting how the charge is cut from the prepreg sheet, so material scrap, offall, can be greatly reduced compared to 090 fabrics where cut pattern orientation is constrained to the biases. By summer of 2022, IDI had some internal success with QISO co-molding trials, including incredible thermal runaway performance in our flame-resistant product, FlameVex. We've also applied the co-molding approach to our epoxy carbon fiber system, Ultrium, as a reinforcement in composite automotive wheels. We were then approached by a global engineering consultancy working with a prominent OEM with an engineering challenge: a lighter, higher performing truck bed, reducing mass, cost, and carbon footprint. This was the perfect opportunity to take Fortium QISO to a real-world application. An exhaustive comparative analysis of options for the next iteration of truck bed design was completed. Alternative materials, geometries, and reinforcements were all considered. The idea that won out showed potential for reduced weight, increased performance, minimal cost impact, and high feasibility. The idea was fairly straightforward: to use a combination of continuous woven product to strengthen key stressed areas of an otherwise discontinuous SMC structure, allowing for a thinner, lighter part. This option meant sticking with compression molding as a process and SMC as a key material, both of which are well-established areas of expertise in the current iteration. Conceptually, by taking several millimeters of SMC out of the part and adding back only a few millimeters of continuous fiber in place of it, you lighten the part. Such a design could reduce SMC usage, weight, and volume of the finished product, also reducing carbon footprint. The SMC reduction could offset the higher cost of a prepreg, meaning minimal cost impact. Of course, the final product would have to yield the same characteristic strength and stiffness of the original design, but with the addition of continuous fibers, could critical impact performance in fact be improved by virtue of the continuous fibers dissipating energy, halting crack propagation. A final key to this would be to demonstrate the ability to repeatably co-mold the continuous fibers in a real tool. Collaborating with the design team, a test matrix was developed. The objective was to establish meaningful models of the SMC and QISO and the combination. Variables included plaque type, such as SMC, QISO, and combination, stack up, overall thickness, how much SMC, how many layers of QISO, temperature. Many tests were run at both room temperature and at 90 Celsius. Directionality. Many tests included 0° and 90° samples cut from the panel. Testing included standard tensile and flex testing, as well as a large-scale impact design. The results of quasi-static testing were used to establish a high-fidelity model of the two distinct materials and their interaction. These models were then refined by comparing their predictions to the actual impact results taken in our impact tester. That impact test is one of our own design. A 5 kilogram mass is suspended from approximately 1 meter high, delivering roughly 50 joules of impact energy. On the end of the mass is affixed a 10 millimeter hemispheric tip, designed to try to cause a rupture in the substrate. Mounted to the drop fixture are two pieces of measurement equipment, a high-speed camera and a high-speed laser displacement gauge. LabVIEW enables us to capture the impact in high-speed and high-resolution detail to study the impact response. Here is an example of one of the co-molded samples, 2 millimeters of SMC and 1 millimeter of QISO for an overall 3 millimeter thick panel. The panel is clamp secured on 3 sides, with one side open for a more complex and interesting deflection response, and for capturing the deflection on camera. An analogous 5 millimeter panel of SMC serves as the baseline of our study. As you can see, there is clear puncture evidence on the impacted A side and significant crack propagation on the B side. As a note, the B side was painted white to facilitate the laser displacement gauge, and it happens to highlight the impact damage quite clearly. This is a condition we would hope to prevent using a continuous fiber reinforcement on the B side. Using a 20% thinner panel reinforced with QISO, the benefits are clear on both A and B surfaces. Besides critical puncture performance, the thinner co-molded panel deflected only 10% further than the thicker control, on average. Remarkable performance knowing how sensitive deflection is to thickness. Manufacturability is another key to success of this concept. IDI worked with key molding and supply partners to test Fortium QISO's moldability in several tools. The conclusion is that QISO can in fact be successfully molded in both simple and complex geometries. Here you can see we overlaid 2 QISO charges on the B side of a deep draw trial tool. This part presented a challenge in that the SMC charge had to be laid down first on the tool, then the QISO charge on top of it. We expected that with no retaining features, the QISO would flow and shift with the flow of the SMC. However, the QISO charges generally stayed in place, and the SMC charges were able to fully flow around them. The A surface appearance was not affected by the presence of the QISO. The B surface and all features fully filled, and the QISO is visible on that side. Preliminary trials were also performed in production tooling. In the bed tool, the QISO was placed on the B side as it would in production and draped up the wall of the tub. The part fully filled out with no A-side witness markings. An interesting result, the ribs on the B side were able to fully fill, despite no SMC on that side. We suspect that the resin in the QISO was sufficient to fill those ribs, but this would mean a resin-rich feature with likely little or no fiberglass reinforcement. So we've noted this as a design consideration in future iterations. If QISO and ribs are included on the same side, ensuring some discontinuous SMC is present to fill those ribs. The sidewall geometry presented many more compound curves and tight corners, a proper stress test of the QISO's ability to conform and flow to the part shape. The QISO was placed on the B side and the part fully filled, again leaving no trace on the A side of its presence. The QISO can be seen on the B side, having followed and shaped itself to all the complex geometries of the part, with no folds or voids detected. This truly speaks to the braided product's ability to drape well in a complex tool. Overall, manufacturability seems highly feasible, even in tooling which was not optimally designed for the use of QISO reinforcement. Returning to our concept, let's have a look at how these studies stack up. We produced a co-molded panel of 2 mm SMC, 2 mm QISO. The combination reduced overall thickness from 5 to 4 mm, a 20% reduction in mass and volume. This also reduced SMC usage from 5 to 2 mm, a 60% reduction. Reduced usage means reduced carbon in the production phase. Reduced weight means reduced carbon in the use phase. That reduction in SMC usage helps offset the cost of the prepreg, minimizing cost impact. Comparing the two in tensile testing, the thinner Fortium QISO reached the same ultimate load as the thicker SMC. In flex, Fortium QISO reached a 25% higher ultimate load. Impact testing saw a major improvement, as you saw, nearly the same deflection, no puncture, and we put a stop to crack propagation. Lastly, using Fortium QISO in combination with SMC in a standard compression molding process seems highly feasible. The QISO behaves well in tooling, its preparation is similar to SMC, has no detriment to the A-surface appearance, and can adapt itself to complex geometries. The flexibility of QISO prepreg could be exploited in other vehicle systems as well. In 2021, IDI demonstrated a panel of FlameVex SMC in QISO. At just 2 mm, it passed the UL 2596 thermal runaway test at the highest test pressure of 1,000 kilopascals. I've shown you the impact resistance as a truck bed. Now invert the picture. You can imagine this as an underbody puncture resistance to a battery enclosure, protecting not only the battery cells, but also the vital liquid cooling systems for battery packs. QISO can also be applied as secondary reinforcement in areas of tight clearances, or in the presence of hinges, mount points, bonded faces, and other high-stressed areas. Add performance, reduce material usage, reduce part thickness and weight. With Fortium QISO, add strength and performance where it's needed. Have confidence that the SMC and QISO will bond through their shared chemistry for a fully consolidated part. Get ahead of design challenges with the ability to perform meaningful FEA simulation through strategic partnerships. Fortium QISO will absolutely empower your next generation of design thinking. Driving meaningful change in the automotive industry is not without its challenges and requires dedication to a transformative vision. I thank you for your time and look forward to collaborating with you on your vision today.